The AI revolution is not running on software. It is running on sand. Silicon, specifically. And the chip inside your laptop and the chip inside a $3 million server rack are more different from each other than a bicycle is from a fighter jet. Most people lump them all together and say, the AI chip. That phrase is basically meaningless, and by the end of this video, you will never use it that way again. We are going to walk through every major category of AI chip, what it does, how it works, why it exists, and where the industry is actually headed. No jargon without explanation, no buzzwords, just clarity. Let's start with something you already know. Your computer has a CPU, a central processing unit. It has been the brain of every personal computer since the 1970s. A modern CPU might have somewhere between 8 and 64 cores. Each core is big, fast, and extremely good at doing one thing at a time. Think of it like a team of 8 brilliant engineers sitting around a table. Each one can solve almost any problem you put in front of them. Flexible, powerful, fast. But here is the thing. Training an AI model is not one hard problem. It is billions of tiny, repetitive math problems. Specifically something called matrix multiplication. You take enormous grids of numbers, multiply them together, adjust them based on results, and repeat. Billions of times. Then billions more. When researchers in the early 2010s tried to train neural networks on CPUs, it was like asking those 8 brilliant engineers to count every grain of rice in a warehouse by hand. Technically possible, practically hopeless. So they turned to something nobody expected. In 2012, a researcher named Alex Krzyzewski trained a neural network called AlexNet that absolutely crushed every competitor in an image recognition contest. Not by a little. By a margin so wide that people thought there was a mistake. What made it possible? 2 GeForce GTX 580 gaming GPUs that he bought off a shelf. Consumer graphics cards that gamers use to run video games. That moment changed everything. A GPU, a graphics processing unit, was originally designed to render video game frames. To do that, it needs to process millions of pixels simultaneously, which means it needs thousands of small cores working in parallel. Where a CPU has 8 to 64 big cores, a modern NVIDIA RTX 4090 gaming card has 16,384 smaller cores. They each handle simpler math, but they all work at the same time. And it turns out that matrix multiplication, the heart of AI training, is exactly the kind of parallel math GPUs were built for. Neural networks run roughly 30 times faster on GPUs than on CPUs for that type of workload. That discovery sent the entire industry in a direction NVIDIA was uniquely ready for. Back in 2006, NVIDIA had released something called CUDA, a programming platform that let developers write software directly for their GPUs, not specifically designed for AI. But over the next 18 years, an entire ecosystem got built on top of it. Libraries like cuDNN and TensorRT. Frameworks like PyTorch and TensorFlow. Both of those major AI platforms are CUDA native, meaning they were written assuming NVIDIA hardware underneath. 2 million active developers have built their workflows on CUDA. Switching to a competitor chip right now means rewriting software from the ground up. That is not a spec advantage. That is an 18-year head start. And NVIDIA used that time well. The H100 is the chip that trained most of the AI models you interact with today. It delivers 989 trillion floating point operations per second at FP16 precision. It carries 80 gigabytes of ultra-fast HBM3 memory and consumes around 700 watts, roughly 4 times the power draw of a standard desktop CPU. A single H100 costs between $25,000 and $30,000. Not to rent, to buy. And for a while, there was a waiting list. Then came the H200, same chip die underneath, but with a critical upgrade. 141 gigabytes of HBM3E memory and 4,800 gigabytes per second of memory bandwidth. For large AI models, memory is often the bottleneck. More memory means you can hold a bigger model in one place without constantly shuffling data back and forth. The H200 runs around $30,000 to $40,000 per chip, and then NVIDIA released the B200, Blackwell, a dual-die chip with 208 billion transistors, 180 gigabytes of HBM3E, and 8 terabytes per second of memory bandwidth. It pulls up to 1,400 watts under full load. For context, that is roughly the same power draw as a small electric space heater running flat out, except it is one chip doing AI math. The B200 delivers roughly 4 times the training throughput of an H100 and costs somewhere between $30,000 and $50,000 per unit. These chips are not sold individually to most buyers. They are sold in racks. A GB200 NVL72 Rack 72 Blackwell GPUs, all connected together with NVIDIA's high-speed NVLink interconnects, runs between $2.8 million and $3.4 million. The next-generation Vera Rubin NVL72 rack, up to $8.8 million per unit. If you cannot buy one, you can rent compute by the hour. An H100 runs about $2.69 per hour on cloud platforms. The B200 sits around $4.99 per hour. Here is a number worth pausing on. NVIDIA's data center segment, the division that sells these chips to cloud companies and AI labs, brought in $51.2 billion in a single quarter. 1 quarter. That is more revenue than most Fortune 500 companies generate in a full year, and it accounts for roughly 90% of NVIDIA's total company revenue. Oh, and NVIDIA's networking division, the cables and switches that connect these chips together, earned $7.3 billion in that same quarter. The cable is itself a billion-dollar business. But NVIDIA is not the only player. AMD has the Instinct MI300X, and its biggest selling point is memory. 192 gigabytes of HBM3 onboard, 2.4 times what the H100 carries, and 5.3 terabytes per second of bandwidth. For very large language models that simply do not fit inside an H100's 80 gigabyte memory limit, the MI300X is the obvious alternative. The hardware is genuinely competitive. The problem is software. CUDA has 18 years of ecosystem momentum. AMD's software stack is catching up, but catching up takes time, and most AI teams are not volunteering to debug software compatibility issues at the same time they are trying to build a product. Now we need to talk about a chip most people have never heard of, quietly built to run the whole show. In 2013, Google ran a calculation. They figured that if every Android user spent just 3 minutes per day doing voice search, the compute demand would require Google to double the size of their entire data center infrastructure. CPUs were too expensive and too slow for inference at that scale. So they launched a secret project to build a custom chip from scratch, one optimized specifically for the matrix math that neural networks require. They expected to build fewer than 10,000. They ended up building more than 100,000 before the project even became public. The paper announcing it was published in 2017. By then, TPUs had been running Google Search, Google Translate, and Google Photos for 2 years. The TPU, the Tensor Processing Unit. The architecture inside it is fascinating. It runs on something called a systolic array. Picture data flowing through the chip in rhythmic pulses, in one direction, then another, the way blood moves through a heart. That design is extremely efficient for the specific kind of matrix multiplication that neural networks demand. No wasted cycles on general-purpose flexibility. Just one thing, done relentlessly, at massive speed. The latest generation is the TPU v7, which Google calls Ironwood. It delivers 4,614 trillion operations per second per chip, measured in BF16 precision. Google can connect up to 8,960 TPU chips together in a single pod using optical circuit switching. A machine the size of a building, running as a single coordinated brain, the TPU v6, called Trillium, was already delivering 4.7 times better performance than its predecessor and 4 times better cost per dollar than the H100 for training large language models. TPUs are not sold commercially. You access them only through Google Cloud. But if you are training a large model on Google's infrastructure, there is a real argument that you are better off on the chip Google built specifically for that task. Now let's come down from the data center and talk about the chip in your pocket. Your smartphone, and increasingly your laptop, has a dedicated block of silicon for AI called an NPU, Neural Processing Unit. These are not built for training, they are built for inference, taking a model that has already been trained and running it locally, on device, without sending your data to a server. The key constraint is power. A data center GPU can pull 1,400 watts. A smartphone chip has to run on a battery smaller than your palm. Apple's M4 chip includes a neural engine that delivers 38 TOPS, tera operations per second. Qualcomm's Hexagon NPU inside the Snapdragon X Elite hits 45 TOPS, and in a 2024 demo it ran a 13 billion parameter language model locally at over 20 tokens per second. AMD's XDNA 2 inside the Ryzen AI 300 series hits 50 tops and qualifies for Microsoft's Copilot Plus program, which requires at least 40 tops. But here's where TOPS gets tricky. TOPS stands for tera operations per second, 1 trillion operations per second. Higher sounds better, but it is a marketing number and you have to read the fine print. First, the precision matters. Chips quote their TOPS at low precision math like INT8 or FP8, which runs faster than the FP32 precision used in some workloads. Second, memory bandwidth, thermal design, and software efficiency all shape what the chip can actually do in practice. Apple's 38 TOPS neural engine consistently matches or outperforms nominally faster competitors because Apple controls both the chip and the software running on it end to end. The number on the box does not tell the whole story. At under 10 watts, the Apple neural engine inside an M4 chip handles AI tasks that would have required a room-sized supercomputer a few decades ago. The same chip that runs Xcode or Final Cut also runs local speech recognition, image segmentation, and on-device LLM features simultaneously without draining your battery in an hour. Remarkable engineering. Now let's talk about the part of the chip industry most people have missed entirely. Every major technology company has quietly started building its own custom chips. Not to sell, for themselves. Because when you are running hundreds of thousands of servers, even a 20% efficiency gain per chip translates into hundreds of millions of dollars in savings annually. Amazon's Trainium 3 chip delivers 2.52 petaflops at FP8 precision. With 144 gigabytes of HBM3E memory and 4.9 terabytes per second of bandwidth. Anthropic, the company behind Claude, trains its models on 500,000 Amazon Trainium 2 chips, one of the single largest private compute deployments ever assembled. Microsoft built the Maya 200, optimized for running inference workloads across its cloud infrastructure. Meta built the MTIA chip specifically for ranking and recommendation models, the algorithms that decide what you see in your Facebook and Instagram feeds. Intel's Gaudi 3 offers 64 tensor processor cores, 128 gigabytes of HBM2E memory, and 3.67 terabytes per second bandwidth, positioned as a more affordable alternative to NVIDIA for certain workloads. And OpenAI, a company that manufactures nothing, signed a $10 billion partnership with chip design firm Broadcom to create custom inference chips. Deployment begins in late 2026. Broadcom is projected to hold roughly 60% of the AI custom chip market by 2027. The era of every AI company running on off-the-shelf NVIDIA hardware is already ending. Here is something that does not make headlines but probably should. Every one of those custom chips, Google's TPU, Amazon's Trainium, Microsoft's Maya, Meta's MTIA, OpenAI's new chip, gets manufactured at TSMC. One company, located in Taiwan. The entire AI industry's hardware supply chain runs through a single geographic point on the map, and the geopolitics around that are complicated enough to make serious people nervous. When U.S. export controls blocked NVIDIA's H100 and H200 from being sold to China, the entire global chip allocation shifted. TSMC's advanced manufacturing capacity is already oversubscribed by 3 times demand. HBM memory, the fast memory stacked on top of AI chips, is sold out from all 3 major suppliers through the end of 2026. And the power problem is real. AI data centers consumed 155 terawatt-hours of electricity in 2025. That jumped 17% in a single year, and it is projected to roughly triple by 2030. A single B200 GPU at full load draws 1,400 watts. A full rack of 72 of them draws more power than a small neighborhood. Tech companies are negotiating directly with utility providers for dedicated power contracts. Some are backing the restart of decommissioned nuclear plants. The chip inside your AI assistant is not just changing software. It is rewriting the energy grid. So let's put this together. CPUs are the general-purpose backbone. Fast, flexible, good at almost everything, but not built for the parallel math AI demands. GPUs cracked that problem in 2012. And NVIDIA spent the next 13 years building a software ecosystem so deep that competitors with better specs still struggle to displace them. TPUs are custom-designed chips that Google built in secret to solve an inference cost problem, and they turned out to be some of the most efficient AI chips ever made. NPUs bring inference to the edge, your phone, your laptop, at power budgets that would have seemed impossible 10 years ago. And custom silicon from Amazon, Microsoft, Meta, and OpenAI is reshaping who controls the hardware underneath the AI industry. Each category exists because a different constraint forced it into existence. The CPU hit a ceiling. The GPU filled the gap. The TPU solved the cost at scale problem. The NPU solved the power at the edge problem. Custom chips solve the control and efficiency problem. The chip landscape is not a ladder where one thing replaced another. It is a map where every region has its own terrain. The next generation of AI is not just about bigger models or smarter algorithms. It is about who can build or buy access to the hardware those models run on. And increasingly, that means knowing the difference between a chip that trains and a chip that infers, a chip that costs $50,000 and a chip that costs $500, a chip that draws 1,400 watts and one that draws 10. So here is the question I keep thinking about. We are at a moment where the hardware side of AI is accelerating faster than most people realize, and the real constraint may not be algorithms or data. It may be power, manufacturing capacity, and geographic risk. Does that concern you? Or do you think the industry will solve it the way it has solved every other engineering constraint? Drop your answer in the comments. And while you are there, which chip type surprised you the most? The fact that AI started on gaming cards, the scale of Google's secret TPU program, or just how much electricity these things consume? Tell me below. If this video helped something click for you, hit the like button. It genuinely helps more people find this channel. Share it with someone who keeps asking you what all the AI chip talk is actually about. And make sure you are subscribed, because next time we are going inside the data center itself, what one of these billion-dollar AI supercomputers actually looks like, how it is cooled, and why some of them are being built underground.